Santosh Gupta and his team for organizing this extraordinary event. And for me, it's multiple pleasure to see many of my old friends here. I do recall my previous visit to this place. I thought it was somewhat more recent, but they remind me it was 7 years ago. I'm happy to be here. I was happy to hear about the progress UPES has made in the course of their existence. I compliment them and I wish them a very bright future. I'm here to share with you, in consonance with the title that you are given, Advances in Chemical Engineering, I made a slight modification of what I had communicated to Santosh, and I said retrospect and prospect. And I'm linking this to chemical engineering for imperatives in chemical, petrochemical and petroleum refining industries. And I'll try and explain to you how charming is chemical engineering, how exciting is chemical engineering, how it serves an industry which has made a major impact on the quality of life. An industry whose global turnover is in excess of $5 trillion. First industry in the world where organized research was done in industry. First industry in the world which got globalized before the word globalization became a talk of the town, so to say. I'll take you back and explain to you many things which become very fashionable these days, but they were integral part of chemical engineering. I do want to tell the young students who are here that chemical engineering has been always an evolving discipline. The half-life of chemical engineer is no more than 6 years. So beware, after you have graduated, keep on reading, otherwise you become out of date. This, I take you back, first legendary thing in the history of chemical industry, and link it without chemical engineering being in existence, what happened. And this was the solvent process for making soda ash. And this supplanted a polluting process called LeBlanc process, and was first instance in the world when His Majesty's Inspector of Alkali ordered closure of a plant and gave birth to a very benign plant, Ernest Solvay, in whose name there is a big industry, Solvay industry. But what I want to explain to you is that Solvay recognized a problem which became a very topical problem in the evolution of chemical engineering, that bubble column reactors where J.B. Joshi has made a seminal contribution. And by ingenious method, he could come to spacing in the large size bubble column reactors, that too made of cast iron, because brine is so corrosive that they had to use cast iron. And the spacing was so imaginative done that with the elaborate modeling that was done, simulation that was done, turned out to be right. It was a source of inspiration. Just to tell you that the applicability of any concept that you have actually bestows us far more rigors in fundamental research. And here is an example of so many things in the same thing: absorption with reaction, problems of heat transfer. Now this is 1865. I then take you to another legendary thing, sulfuric acid. That was the first important catalytic process. But from chemical engineering point of view, what came many years later, adoption of adiabatically operated multiple fixed beds. So then now you talk about hierarchy of multiple fixed beds and all that, but this was in existence in very early part, still before formal discipline of chemical engineering was recognized. And how principles of thermodynamics, undergraduates normally have a little bit of disdain for thermodynamics, particularly when it is not taught properly. But thermodynamics is so critical for chemical industry, and here was an example that you wanted SO2 conversion to be almost 10% so that no unreacted SO2 goes, and use of excess oxygen was the first part, but later on, double contact, double absorption. So intermediate level after 2 beds, you remove SO3 so that it is out of sphere of action and you are able to take the reaction to completion. We used to emit 5,000 ppm SO2 in atmosphere. Today it is next to nil. That is what was done, and look at the concepts of chemical engineering ingrained such a long time ago. Now I take you to the most outstanding development in the history of chemical industry, Haber-Bosch ammonia process. Again I am going to explain to you how by now chemical engineering was born. But Haber was a physical chemist. And both Haber and Bosch, the only time an engineer got a Nobel Prize was Bosch. And what are the concepts that were ingrained in this Haber-Bosch process? First, to show how demanding is innovation, Haber tested 5,000 catalysts. And after more than a century, that catalyst still stands test of the time. Some modifications are there, but the basic structure of the catalyst is same as was in 1910s. But I want to emphasize on the concepts. First of all, at that time, thermodynamics was not so well developed that you could predict non-ideality with any precision. So Bosch cranked out the non-ideal behavior of nitrogen and hydrogen at very high pressures going all the way up to 1000 bar by experiments. And it turned out that non-ideality was very useful in terms of giving you higher conversion. But what were the concepts that came, which became ingrained in the history of chemical industry? First was total recycling. And that you had to use nitrogen and hydrogen in strict stoichiometric ratio of 1:3. And conversions were only 15%. And you had to have complete recycling. The concept of purge gas also came at that time because nitrogen contained argon, and argon keeps on building. So for the concept of purge gas also came at that particular time. Now today you may be talking big thing, purge gas, but I am talking about a concept more than a century ago when purge gas was ingrained into an ammonia loop. Nitric acid was an outstanding example. As a matter of fact, ammonia came first because one needed nitric acid. One needed nitric acid because you cannot have explosives without nitric acid. TNT and all host of explosives depend on nitric acid. But look at the charming part of this, that ammonia is oxidized to NO with platinum rhodium gauze catalyst. And in a 1,000 ton per day nitric acid plant, the size of the reactor is so trivial, but the chemical engineering is very intricate. There was a word called CFD at that time. But engineers were very ingenious and they could mix ammonia and air so thoroughly, otherwise there will be malfunctioning of the gauze reactors, they will be flickering, and it will also lead to more loss of platinum. So the perfect mixing of ammonia and air into the reactor was done long before CFD came into existence, and which has become extremely important in chemical engineering. The other one was when you are taught physical chemistry in undergraduate days and you are said first order reaction, second order reaction, third order reaction, you normally dismiss third order reactions saying, oh, this like looks like a fancy. Here is a concrete example of an industrial practice where the pressure for absorption was taken from 1 bar to 10 bar, and that resulted in 10⁻⁴,000-fold reduction in the volume. By the way, stainless steel was born to meet the corrosive nature of nitric acid at that time in Sweden, where Nobel did all his work. Then came urea. Here also large size bubble column reactors are used, and they were designed in those days without all the concepts that we have today. But again there were thermodynamic limitations, and total recycle of ammonia and carbon dioxide had to be done. Now this has been there for a long time. Now since I mentioned to you that it is a highly science-based industry only next to nuclear, I want to tell you how in history of chemical industry, the most outstanding example of a discovery-driven product is nylon 6,6 polyamide. As you know, Nobel Prize is not given posthumously. So Carruthers never got the Nobel Prize because he died and actually committed suicide. Now, here something most original was done to make hexamethylene diamine. In lessons in organic chemistry, when you are taught Markovnikov principle, anti-Markovnikov principle, first outstanding example of anti-Markovnikov reaction was HBr addition to butadiene, so that you get bromine in the terminal position, which then you convert into amino group. So hexamethylene diamine was made by invoking anti-Markovnikov rule. But chemical engineering required separation of unwanted isomers. Later on, when polyester was born around the same time, 1930s, polyester was the first thing where, only time I would say, where the chemical terephthalic acid was classified as PTA, purified terephthalic acid. Ethylene glycol, which was originally produced as an antifreeze because the radiators would freeze, water would freeze. So glycol was added to water as an antifreeze. That time they did not know that ethylene glycol will become such a huge product for the purposes of polyester fiber. But they are ultra high purity, and these purities are higher than analytical reagent grade chemicals. That is another lesson that sometimes you think industrial products don't have. Today you talk of very high purity. In pharma industry, nobody talks of purity. They only say, give me the impurity profile. 99.9% is taken for granted, but give us what is that 1000 ppm built up of. So we are producing ultra pure chemicals on very large scale as well as on very small scale, some molecules which are produced on very small scale. Then came another breakthrough, and I want to tell you how the polluting processing. Today you are talking a lot about fashionable thing, green chemistry, process intensification. I am going to convince you that all these have been integral part. Ethylene glycol was made from ethylene oxide in turn made by the polluting chlorohydrin process, and it got converted to direct oxidation of ethylene to ethylene oxide. Here was the example, phenol was made by benzene sulfonation alkali fusion, benzene chlorination alkali fusion, completely replaced by cumene oxidation in very large size bubble column reactors. Very large size bubble column reactors, whose design principles at that time were in a nebulous stage. And the concept of multiple circulation cells, where J.B. Joshi was involved, was introduced only in 70s, whereas this was in operation in late 50s, early 60s. To demonstrate to you, many times practice precedes theoretical work or engineering science work. This happened even in fluidized bed reactors during second war for cat tracking. The large size fluidized bed reactors were put in place without having the concept of two-phase theory in fluidized beds. So remember that sometimes practice precedes, but most of the time you need very sound background to design. Next, we had polluting processes for reduction of aromatic nitrocarbon, like anything. Any is a multi-million ton product, like phenol is multi-million ton product. They were all done with chemicals, so they were polluting. Today we do in a neat way by hydrogenation. But what is the development in this? You look at the design of hydrogenators in terms of different types of hydrogenators, whether they are trickle bed or whether they are CSTR, and very important development took place to gas-inducing impellers, on which a lot of work was done in ICT in 17, and large number of hydrogenators in India have come out of the work from ICT led by J.B. Joshi. They consume less power and give extraordinarily high quality mixing, gas-liquid mass transfer coefficients. Gas-inducing impellers have been introduced in the large scale for large number of hydrogenations. And the design of trickle bed reactors actually started when there was a need for fuel oil desulfurization. Just to remind you, whole of Europe, central heating or heating in homes was done by using fuel oil, and each house was emitter of SO2, because this fuel oil could contain 0.5%, 0.6% sulfur. And there was a need to do hydro desulfurization of fuel oil. And this was a large-scale operation. That was the first time in history of chemical industry that fixed bed hydro desulfurization units were designed. The exciting part was, if you were to remove sulfur down to such an extremely low levels, nobody recognized in the beginning the role of back mixing. And they were liberally designed. Now today, you know, liberal designs means a lot of extra money, and one doesn't want to do that. So principles of chemical engineering have allowed the capital cost to be kept down. Again, acrylonitrile in 16, by hemooxidation of propylene, displaced a hazardous process of acetylene plus HCN. The funny part was, in making acrylonitrile from propylene, HCN came as a byproduct at the level of 6 to 7%. So you used to say roles were reversed. But what it meant was, first time in the large-scale fluidized bed reactor was used for hemooxidation of propylene. By that time, principles of designing fluidized bed reactor came very handy. But extraordinary development took place in 70s, about which I'll make a reference later, when in the initial literature of fluidized bed, you can read all the papers in late 40s, 50s and 60s, you will never find a reference that fluidized bed reactors could be used for polymerization. 1970s saw linear low density polyethylene being made in fluidized bed polymerization reactors, where capacity could be in a single reactor 1,000 tons per day. It changed fundamentals of business. What I want to tell you, there are many things in the history of chemical industry which changed fundamentals of business. Here was an example: an overnight acrylonitrile price came down to 1/3 of the earlier price, and old plants were thrown out completely. Similarly, hydroformylation of olefins was done at low pressure, which was in contrast to earlier processes which were at 200 to 300 bar. But I'll explain to you something interesting that happened in the case of hydroformylation of olefins, where chemical engineering principles came very handy, and I'll explain to that in a while. These homogeneously catalyzed reactions of hydroformylation, carbonylation, etc., the catalysts, they are the largest scale homogeneously catalyzed reactions. The question comes, when you use expensive material like rhodium and all, what is the cost of loss of rhodium? And they are scarce. They are not available in abundance. And novel chemical engineering concepts have been used. First, not only large-scale bubble column reactors have been used, there have been concept of using two liquid phases. This same rhodium phosphate catalyst was made water soluble by sulfonation, so that the catalyst recycling was done by a biphasic system. It's a new concept in chemical engineering. But there was another process where oligomerization of ethylene was done, again in large size bubble column reactors, but with two liquid phases. The second liquid phase was a solvent in which the product was insoluble. So it was very easy to recycle the catalyst. So hexene, octene were all insoluble in 1,4-butane-diol, and this was another concept of recycling introduced by and large for the first time. Now, there are some instances where we have extraordinary achievements, and how a major liability has been converted to an extraordinary asset is removal of H2S either from sour natural gas or all from hydrodesulfurization plants. And there is no way other than absorption with chemical reaction for H2S to be removed. But what is extraordinary in the design is your feed gas might contain few percentage of H2S, sometime in some sour natural gases as high as 20% in Canada. And the exit gas must not have H2S more than 1 ppm or even less than 1 ppm. Now imagine challenges in chemical engineering to design these absorbers where you have levels of conversion. When you learn principles of residence time distribution and you talk of 95%, 98% conversion and how back mixing matters, even in packed columns. Now, if you want less than 1 ppm of H2S, how astute should be that design, recognizing principles of back mixing even in a fixed bed absorber, back column absorber. So here was an example. Now, CO2 in contrast to H2S removal, where absorption with chemical reaction is indispensable. All CO2 streams used to be originally with physical solvent, which was very, in fact, you will be surprised, there were plants in 1930s and all, CO2 used to be removed under pressure in water. Nothing could be worse than that because solubility is so low. Then some physical solvents came. Still, the productivity was too low. So absorption with chemical reaction became the order of the day. But here comes a tectonic change. Pressure swing adsorption allowed CO2 to be removed even in ammonia plants and get CO2 of a purity which is good enough for urea plants. Now you can imagine how an existing well-established process underwent what I would call a tectonic change, that you could dispense with CO2 removal by absorption with chemical reaction and just use pressure swing adsorption. And pressure swing adsorption came in, which really gave chemical engineering a big boost because these designs could not be done without very elaborate simulations because the cycles are very short. Nobody could design pressure swing adsorption columns done originally for nitrogen. CO2 came much later. And zeolites made a big difference in terms of pressure swing adsorption. Today, pressure swing adsorption is being adopted on grand scale for many things. But this was the first instance, and we needed many inputs of chemical engineering in this apart from simulation. The thermodynamics of adsorption in multi-component system. I think Rakesh Agarwal will remember how people in air products did very elaborate work. Sarkar did very elaborate work on thermodynamics of adsorption of multi-component systems and so forth. I will now talk about what kind of dramatic changes are going to come. And I'm now going to refer what transpired during tea time. The tectonic change in petroleum refining, the consumption of fuels is coming down because of more efficient car based on petrol, based on diesel, and large number of vehicles moving to CNG. It is leading to reduction in consumption of petrol as well as diesel. And one is seeing this trend, even in India, globally it has become very prominent. And battery operated things will make further difference. And renewable energy is giving you energy-based system, yet another one. And I'll talk about chemical engineering contributions in that area shortly. And this would require, why I am referring to this and what are the challenges chemical engineers will face in this great tectonic change, smart chemical engineering for reliable operation and valorization of all fractions. If you consign, in a fuel refinery concept is something which is not good, at least you can burn it. So even asphalt can be burned. But that is the waste. And of course, then you talk of more CO2 emissions, and this is all of the day, climate change depends on CO2 emissions and all that. This is something which is going to demand very smart chemical engineering, concepts of astute scale-up, and very acute separation problem. And I'll give you some flair of this. How in a cat cracker, when a lot of butenes come, butene one is a co-monomer, how 2-butene can be valorized by metathesis with ethylene, this is commercial. Although reverse of it was the one which was practiced earlier. How specialty chemicals can be made from butadiene, like telomerization, not telomerization. How butadiene has given not only nylon 6,6 to hexamethylene diamine, but the trimerization of butadiene to cyclododecatrine, cyclododecane, nylon 12, C12 dicarboxylic acid to give both polyesters as well as polyamides. You might have heard of recent incidents that one plant blew up and automobile industry was badly affected because nylon 12 was not available. Nylon 11 came from castor oil. Smart separation of C5 fraction. The C5 fraction contains piperylene, isoprene, cyclopentadiene, and isoamylene. These separations are not easy. They require very elaborate chemical engineering. And couple of companies only in the world have that expertise. And we need to develop that expertise in India. In all cat cracking, a large amount of LCO comes, light cycle oil. India is a huge importer of naphthalene. And there is a new polyester called PEN, P-E-N, polyethylene naphthalate, which has very high barrier properties and it can be even retorted. And that requires 2,6-dimethyl naphthalene, very pure. Imagine separating 2,6-dimethyl naphthalene from all other isomers. And look at the problems of chemical engineering you will face in valorizing naphthalene, alkyl naphthalene, dimethyl naphthalenes from light cycle oil. So here are challenges for chemical engineers in the forthcoming. All naphtha cracking has been done steam cracking thermally. It's one of the rare non-catalytic processes in the chemical industry. But now it is a strong candidate for a catalytic process. What does it bring in the wake of chemical engineering? That how will you cope just as fluidized bed reactors could cope for cat cracking? This is even more demanding than cat cracking operation. So the design of these fluidized bed reactors would require far more astute work than one is inclined to believe. I will now move on to a major breakthrough that came through membrane separations and how chemical engineering has made such a great impact on the quality that everybody in the street knows RO. Everybody knows RO. And the breakthroughs came in when we had hollow fibers and how it has made an impact on quality of life not only for water but for the kidney patients. The dialysis is done with the very membranes that were developed for chemical industry. These membrane cells have also become dominant in making electrolytic caustic soda because they are based on perfluorosulfonic acid. They can stand 30%, 35% caustic soda and chlorine also. Now, what it does, that first time you saw importance of catalyzing electrochemical processes, anode as well as cathode. Now this is a new thing and I'm going to tell you how electrochemical engineering is going to come into a kind of a central play. Why? Because you can have a distributed system with solar power, wind power, you can put electrolytic hydrogen, you can put through power air separation to pressure swing, get pure nitrogen, you can put small capacity ammonia plant. Now look at the kind of design principles that we have evolved to have 25, 30, 50 tons per day of ammonia using only renewable energy, hydrogen by electrolytic process, nitrogen by pressure swing adsorption. So you are going to see a lot of, the other things that happen in chemical engineering was combo processes. They were real advance in chemical engineering because when, for example, distillation, when you have reactive distillation, you combine reactions with distillation, cut down the capital cost, cut down the energy cost, and the major impact was made first with methyl acetate, then with MTBE. All MTBE were reactive distillation columns later on, and that most of them use cationic ion-exchange resin as catalyst. The largest single application of cationic ion-exchange resin has been in making MTBE and later on tin. Reactive extraction, the birth was in nuclear industry because uranium ores are very lean, and to valorize this, you need reactive extraction. And you will be surprised that major part of the work in reactive extraction in the world in hydrometallurgy has been done by chemical engineers, whether in Canada, US, South Africa, Australia, not by metallurgical engineers. So you can see how versatile chemical engineers are in doing these kinds of things. A more recent development is reactive adsorption. And I would think that in coming years, you will see some more work on reactive adsorption. I'll now proceed further that why we need smart crystallization. I'll dramatize this. In all API, the pharmaceutical industry, active pharmaceutical ingredient, practically all of them are crystallized. So you can put up a plant where organic chemistry is right, everything is right, but product is not sellable. Why? The particle size distribution is not right, loss on drying is not right, impurity at ppm level is not right. All because crystallization is not done properly. You may have bulk density of 0.4, but you want 0.6. Now chemists are not familiar. There's only chemical engineers who are able to tackle this problem. And personally, I handle many such problems. But I'm telling you, there is an acute shortage of smart work in India on crystallization to give you, I'm not talking about polymers, I'm just talking of crystallization to give you right bulk density, right loss on drying, right impurity profile. And this is something very demanding. Then whatever was done in batch processes, particularly for hazardous reaction, the micro-reaction engineering has come, micro-reactors, what chemists call flow reactors or flow processes, that are bringing in new concepts in chemical reaction engineering. Because when chemical reaction engineering was first introduced in late 50s, those concepts were different. What now we need in advances in chemical engineering, new concepts. The adoption of CFD is being done in a big way these days because you cannot have large-scale designs without astute scale-up, and that cannot be done without CFD. So much more CFD will be used in chemical industry than has been used in the past, for sure. Process intensification byword these days, but I want to explain to you that has been an integral part of chemical industry from the beginning, starting from such a simple example as replacement of rashik rings with bulk saddles, interlock saddles, ball ring, then structured packing, bubble cap plate being replaced by C plate, valve ring. They were all heat exchangers. When plate heat exchangers came, they were all examples of process intensification. AdChE contactor that came gave the values of gas liquid mass transfer coefficient extraordinarily high. And this AdChE contactor is today commercially used. One of the areas in which we made some contribution, my collaborator G.D. Yadav did some work along with Lahiri. And this chlorine absorption in caustic soda, stripping out HOCl, seeing smart chemical engineering of what happens in a diffusion film. What happens in the immediate vicinity of the interface that you can strip out HOCl even if caustic is in excess. And this is commercially practiced. The replacement of Russian impellers, which itself was an important development, and Rakesh might know that Russian impeller came from Purdue. And today we have impellers of such smart designs which consume less power and give you far better mixing. I referred to you earlier about gas-inducing impeller, but I am now talking of impellers of new design which consume less power and still give you much higher values of heat transfer coefficient and the values of mass transfer coefficient. When static mixers came in, this was a clear example of process intensification. And of course, academics are very smart. How do you get funding? Today the bandwagon is process intensification. Put the title process intensification or green chemistry. I'm trying to convince you that they've all been integral part of chemical industry all along. Now, many more examples can be given. Physical extraction replaced by reactive extraction for dilute acids. How do you recover 1 or 2% acetic acid? You can't distill because energy cost will be exceptionally high. So you adopt reactive process. Then when you use smart thing, marrying reaction kinetics with the principles of mass transfer with chemical reaction, mixture of phosgene and carbon dioxide being absorbed, people were foolishly absorbing this mixture in caustic soda and consuming huge volumes of caustic soda only to destroy COCl2, not recognizing that COCl2 hydrolyzes with water with half-life of 1/25th of a second. So you can just remove 99.9% phosgene only by water scrubbing and save a lot of caustic soda. My purpose of mentioning this is to show how you marry principle. Chemical engineering is the only branch of engineering which hinges on chemistry. No other branch of engineering has this mooring on chemistry. Then intensification to ultrasonification, which A.V. Pandit has made seminal contribution, both through cavitation and standard ultrasonification. But photocatalytic reactions will become, because what has happened with availability of renewable power, photocatalytic reactions, then nano-precious metal-based catalysts. This is a very outstanding example that when people understood that noble metals can be narrow size, particularly gold. Not only you save on noble metal cost, but you also improve the efficiency. It was first recognized when people realized, right from Aribel day, that gold doesn't work unless it is nano. It is here that the people found that gold, if it is not nano, it doesn't work. Here is an example of nano having an issue. What are the other new concepts that we need to attune ourselves? Formulation engineering, product engineering. I expect some chemistry departments to introduce formal courses in formulation engineering, product engineering, new concepts in chemical engineering for lubricants, detergents, creams, ice cream. I quote ice cream as an outstanding example how principles are used of interfacial sciences to sell air and water, and you make big money selling ice cream. How microemulsions are making a big impact, including drugs for infants, pediatric drugs, because they are thermodynamically stable, they don't separate into phases. How micellar catalysis can be invoked in many processes. What are the challenges that we face? What will be the next major change that comes after shale gas? It will be the exploitation of natural gas hydrates. Imagine chemical engineering implication in exploitation of natural gas hydrates, fire on ice, as they say. And very new concepts in chemical engineering could be required. So is it for underground coal gasification, which is environmentally very, very desirable. Large-scale biotechnology is going to come in a very big way, but not loose way in which it is being taught. I'm talking of hardcore biotechnology, biochemical engineering, and how CO2 going to methane, hydrocarbon, alcohols, difficult biotransformation. J.B. Joshi tells me that he is able to get KLAs all the way up to 1 reciprocal second. Normally we are tuned to not more than 0.1, and we are now talking of 1. Now there is nothing but chemical engineering principles being used, and if you want large scale output, then you have to have high values of mass transfer coefficient. But adoption of directed evolution of enzymes is going to, our engineering biology is going to make. And I urge all chemical engineers to read the paper of Nobel laureate Francis Arnold, where you are projecting a future that we will be able to even excel nature if to do the directed evolution. And I project a very bright future for chemical engineers in this area. And fermentation products, other than many known products like human milk oligosaccharides, linking of two different amino acids, new biopolymers, and here you need background, strong background of biology, but without chemical engineering it's not possible. Remember when penicillin came in, large-scale production of penicillin critically depended upon gas liquid reactors giving high values of KLa. Without that, penicillin production could not have been increased. Economic processes of valorizing bagasse and cellulose. Bagasse is the single largest renewable material available in India. And if you get alpha cellulose, hemicellulose, lignin from it, you can change the dynamics of chemical industry because a lot of phenolic substances can come from valorizing lignin. If you do fluidized bed conversion of lignin, new principles will be born, and cellulose-based plastics will come back in a big way. One of the best ways of valorizing CO2 is dry reforming of methane, which is almost now around the corner because it requires stability of the catalyst. How we can convert hydrogen to oxygen directly to hydrogen peroxide. Number of scientific papers have come. A lot of chemical engineering will be involved in designing these reactors once the catalyst part is sorted out completely based on palladium. And like that I can. But let me tell you about, since huge amount of ethane is available from gas fields as well as from shale gas, direct conversion of ethane to acetic acid plus ethylene and then to vinyl acetate can change fundamentals of business. Urethanes without forcing, oxidation of paraxylene to purified terephthalic acid where hydrogenation of aldehydes is not required. Amount of capital investment that goes in removing parts per million of aldehydes to make purified terephthalic acid is exceptionally high. And if you can eliminate that, similarly, get over synthetic natural rubber because land resources will keep on shrinking and go for synthetic natural rubber which will demand isoaniline recovery from the C5 fraction of naphtha crackers, cat crackers and dehydrogenation to isoprene followed by polymerization. Newer catalysts for polymerization. You can see dramatic improvements, whether metallocene and others. First major breakthrough you saw with Ziegler catalyst, but this process of getting new catalysts, I've come across a recent paper where isobutyl vinyl ether has been polymerized with new catalysts which will give a range of products which are absolutely unique. Then in adsorptive processes, how MOF and COF can make a big difference even in catalysis because they can give you areas as high as 3,000 square meters per gram. And I already referred to you earlier about how distributed ammonia plants can come on the basis of renewable energy. They will require completely new principles of chemical engineering. And how fine chemicals manufactured through electrochemical processes where both anodic and cathode. Electrochemical engineering was very popular in 50s, 60s, then it went in oblivion. But I dare tell you that is going to come in a very prominent way in coming years because of availability of renewable energy. And I would therefore say, valorizing plastic waste, about a reference has been made. Whether you crack them to olefins or even you get oil which can be co-cracked with naphtha, it will make a big difference. It's a very serious problem today. And recovery of rare earths from different sources, including phosphogypsum. Coal ash utilization is a huge challenge for chemical engineers because we'll be producing 1 million tons per day in the near future. They are kind of problems. How you valorize these? Can you valorize the cat cracking catalyst? Producing thousands of tons as waste. Can we not make zeolites out of it? Can we not do something more useful? Can we not recover the rare earths which go into cat cracking catalyst? These are the kinds of problems. So, my dear students and eminent chemical engineers here, chemical engineering is never short of challenges. It will never be short of errors. And ingenuity of individual chemical engineers and collective thing can take us to various places. So advances in chemical engineering will continue to happen. You can have the same title for seminar 5 years later, 10 years later, and you will keep on hearing about completely new things. Like I always tell, the number of younger generation fellows will know slide rule. And if they see slide rule at home, then the young fellow will say, what is this? And we guys all grew up using slide rule. Then came calculator. We were doing plate-by-plate calculation of this. I remember when my final year doing several hours we go in doing single plate-by-plate calculation. Now you can do in a flick. So there are things which are changing so dramatically, but so is the demand. And sometimes we take for granted like heat transport coefficient agitated vessels based on old equation, based on flimsy, and we use it religiously. These are open to condensation of vapors which go into two liquid phases, the heat transfer coefficient goes down by a factor of 4. There is no worthwhile research going on. So there is no dearth of topics of great scientific rigor, chemically science rigor, and practical utility. So it's a fantastic field. Enjoy chemical engineering. Celebrate chemical engineering.
Thank you so much, sir. It is always a pleasure and honor to... Thank you, sir.